Greetings, everyone, and welcome to section 9.1, first order linear systems. Okay, a system of differential equations is a set of multiple differential equations that must be solved to find multiple solutions. So we're going to be given a pair of differential equations that look like this. And the first one will say the derivative of function 1 is 4 times function 1 plus 2 times function 2. And the derivative of function 2 is minus function 1 plus function 2. And we are tasked with finding the pair of functions that satisfy both conditions. Now, for this example, what we're going to do is we're going to show that function 1 and function 2, as defined here, solves that system. Okay, so you take a look. If x1 is equal to minus 2c1 e to the 3t minus c2 e to the 2t, sorry about that, then what's x1 prime? X1 prime, taking the derivative of this, we get minus 6c1 e to the 3t minus 2c2 e to the 2t. Okay, and what's x2? X2 is c1 e to the 3t plus c2 e to the 2t. So x1, 2 prime equals 3c1 e to the 3t plus 2c2 e to the 2t. Okay, now that we have each of those, we can substitute them into the set of differential equations and confirm that the left side is equal to the right side. So x1 prime is minus 6c1 e to the 3t minus 2c2 e to the 2t. And what we're here to do is show that this is equal to 4 times whatever x1 is. Write x1 in a different color. x1 is minus 2c1 c1 e to the 3t minus c2 e to the 2t plus 2 times x2. What's x2? Write it in a different color. It's c1 e to the 3t plus c2 e to the 2t. Okay, not only do we have to demonstrate that, which shouldn't be that hard, we get what? Minus 8 c1 e to the 3t minus 4 c2 e to the 2t plus 2 c1 e to the 3t plus 2 c2 e to the 2t. So combining like terms, minus 8c1 plus 2c1 e to the 3t is minus 6c1 e to the 3t. Negative 4 plus 2 c2 to the 2t is that right there. So this is a true statement. So we're halfway home. But we have to show that x2 prime is equal to, so x2 prime, that's 3c1 e to the 3t plus 2c2 e to the 2t equals negative, okay, what's negative x1? Negative x1, that was in red, is minus 2 c1 e to the 3t minus 2 c2 e to the 2t plus, what's x2? x2 is in green, that's c1 e to the 3t plus c2 e to the 2t. Distributing the negative, that's 2c1 e to the 3t plus 2c2 e to the 2t plus c1 e to the 3t plus c2 e to the 2t. Like term, 2c1 plus c1 is 3c1. 2c2 plus c2 is not 2c2. What did I mess up? Agree red function minus 2c1 minus c2. So this is a 1. There we go. So minus the negative is plus. There we go. c2 e to the 2t plus c2 e to the 2t is 2c2 e to the 2t. All right. So basically, all I've done is the equivalent of saying we want to solve something like x minus y equals 2 and x plus y equals 0. Find the x and y that make that true. And the problem says, well, try x equals 1, y equals -1, and show that that's a solution. And that's really all that we've done, just a more glorified version of that example. Okay, so you'll be doing problems like that. In addition, we'll make use of this very powerful theorem. It says any nth order linear differential equation can be written as a first order linear system of n differential equations and vice versa. So we'll do an example showing each way, demonstrating each way of that theorem. So what you have here is a third order differential equation. Okay, what we're going to do is convert that to 3 first order differential equations. Okay, so that means we're going to come up with 3 functions, x1, x2, and x3, that kind of look like that, except for in this one there was 2 unknown functions. Here there would be 3. Here's how we do that. Okay, let's let x1 be defined as y. So let x1 equal y. Okay, that means that, and x2 be the derivative of y, and x3 be the second derivative of y. So x1 prime is equal to y prime, but x1 prime by the transitive property of equality means is equal to x2. x2 prime is equal to y double prime, but y double prime is equal to x3, and x3 prime is equal to y triple prime. Again, I'm just taking derivatives over here. But y triple prime is equal to, well, it's y triple prime. Okay, so let's see what I have here. Taking this equation right here and substituting in the appropriate values, I can say that 3 times y triple prime, so that's 3 times x3 prime, plus 7 y2, or y double prime. Well, y double prime is equal to x3 minus 2 sine t of y prime. Y prime is x2 plus e to the 4t times y, that's x1, is equal to t cubed. Okay, if I were to solve this equation for x3 prime, I would get x3 prime equals, so let's subtract 7x3, divide by 3, add 2 sine t and divide by 3, x2, and add, subtract 1/3 e to the 4t x1 plus 1/3 t cubed. Okay, so that's an equivalent statement of that line. So I promised a system of 3 equations and 3 unknowns. So let's look at x2 prime. x2 prime is equal to, let's say 0x1 plus 0x2 plus 1x3, isn't it? Okay, because x2 prime is equal to x3, so x2 prime is equal to x3. If I had my life to live over again, I probably would have written it as 1x3 plus 0x2 plus 0x1, just so that it matched the order of the x3, x2, the descending order of x3 prime. And then what? x1 prime is equal to, 0x3s plus 0 is 1. Right. x1 prime is equal to x2, so it's equal to 1x2 plus 0x1. And there's the system. Seems a little unnatural, doesn't it? But the theorem guarantees that this third order differential equation can be written as a system of three first order differential equations, and there's your system of three first orders. Okay, but what it also guarantees is that the other way is true. So here's a system of two first order differential equations. We can write it as one second order differential equation. Okay, so this is the other way, the other side of the theorem. Here's how you do that. Okay, first off, take one of these functions and take its derivative. So I'll do the top one just because it's listed on top. x1 double prime is equal to 2x1 prime plus x2 prime. Okay. Now, we can substitute out x2 prime with the information in this line. So x1 double prime is equal to 2x1 prime plus x2 prime. And x2 prime is equal to negative x1 plus 4x2. Now, I know I have functions of t. That's kind of redundant. We don't need to know that they're functions of t. But I'm just kind of being lazy with my notation here. And you can be lazy as well. That's x1 double prime is equal to, combining like terms. Well, there isn't any like terms. 2x1 minus x1 prime minus x1 plus 4x2. Now, if we substitute x2 out of this and write this simply in terms of x1, then what we'll have is a second order differential equation, there's the second order, of the function x1. So let's see, can I do that? Well, yeah, I can, because if you look back in this bit of information in the equation x1 prime, you can see that x2, make sure you're in the window, yeah, x2 is equal to x1 prime minus 2x1. So I'll write that in red here. Okay, using this piece of information, you can say that x2 is equal to x1 prime minus 2x1. And substitute that there. So x1 double prime equals 2x1 prime minus x1 plus 4 times x2, which is x1 prime minus 2x1. Now, this second order differential equation that's below the green line is entirely in terms of x1. Okay, let's combine all the like terms. x1 double prime equals 2x1 prime minus x1 plus 4x1 prime minus 8x1. So that means x1 double prime is equal to 6x1 prime minus 9x1. In other words, that x1 double prime minus 6x1 prime plus 9x1 is equal to 0. Now, just to make that clear that this is a second order differential equation, let y equal x1. Then what's y prime? And what's y double prime? Well, making this substitution in red, this is y double prime minus 6y prime plus 9y equals 0. And there is your second order, your one second order differential equation. So the problems in section 9.1 are of this nature, okay, where you're either verifying a pair of solutions solves a system of differential equations, or you're converting back and forth between an nth order differential equation to a system of n first orders, or you're taking a system of n first orders and converting it to an nth order differential equation. Okay, so there's an example of each. We'll use these facts from 9.1 moving forward in 9.2, 9.3, and so on.